Hello students, today this video is going to be on the formation of the solar system. The picture in front of us is an artist rendition, but it is not far different from our understanding. You notice that there's a few little blobs of stuff in this, basically a small flat rotating disk. So we talked about this in chapter 7. What do we have to explain with a theory of solar system formation? And that is, motion of the large bodies has a pattern. Everything goes roughly in the same direction. We have to explain that there are two types of planets. And we have to explain where all these small objects came from. And we kind of also need to explain the exceptions, because they're exceptions. We need to explain why the rules apply to everything else and not to, say, the rotation of Uranus or Venus or the Earth's moon. And so there's a couple of different theories. Right? It's not a uniform thing, but we've kind of closed up on one theory being the most workable, in the sense that we can, it doesn't explain everything. And I've sent you some notes, adjustments we need to make the other, make this theory work. But, we have the idea of the nebular theory, which is that the solar system formed when the sun formed out of the nebula that the sun formed out of, the solar nebula. So it's a giant cloud of gas that collapses, and as it collapses, the sun forms, but the planets also form. So this is an interesting theory. It's a fairly old one. It's a couple hundred years old, and it was proposed by kind of an unusual duo. Laplace is a mathematician, so that makes sense. Kind of. Kant is a philosopher, and if you study philosophy, you'll hear about Kant at some point. He talks about what's called the categorical imperative. Basically, things are right and just and moral because they're right and just and moral. Like the universe makes it so. So he kind of did think about the universe a bit, but philosophy has evolved a bit more. And of course, it builds on everything that's been before. So anyway, he came up with this theory not as an astronomer, but there's a lot of evidence that supports the theory, and it's something we can work with. Now, there is another one, what's called the close encounter hypothesis, which is the idea that the sun forms and then the material that forms the planets is ripped away by an encounter with another star. There's some problems with that. It doesn't explain the patterns in the motion very well. It doesn't explain all the details. And it's not clear what mechanism would cause that, and not just like either reform the sun or blow it completely apart. Right? It's a more difficult theory to work with. And basically the consensus is the nebular theory probably explains the formation correctly, or more correctly than others. Of course, I've sent you the information on things like the grand tact hypothesis and the small Mars problem. And that stuff, there's problems in the nebular theory, but it can be modified. It can be adjusted so that we can kind of figure out how the solar system looks the way it does today. So where did the solar system even come from? What is this nebula? Here's a picture of a different nebula that is forming. I do not remember what that nebula is, but it's very pretty, I think. But the gist of star formation is something called galactic recycling. Stars form from old stars. What happens is material is formed, and it's in these large clouds of gas and dust. The original uh, clouds were formed in the Big Bang, but new clouds are formed when a star dies. Star dies, it gives material back into space. Either it supernovas and just blows up, or it just pushes off its outer layers. And so you get this material that forms nebula, clouds of gas and dust. And then those clouds collapse and form new stars. And those new stars go on to burn fuel and then expel more matter out into space and make new clouds. And so we can see different stages of stars forming that gives us a reasonable belief that this is what's going on. Is that we can see stars at different stages in this life cycle. So the planets have this orderly pattern. Why did the planets even orbit? Why did they have to orbit or they just fall into the sun. But why are they all going around the same way? Well, whatever this cloud of gas and dust is doing, it is probably rotating around some point. Right? So when it collapses, what we observe in other forming uh, systems is that the cloud collapses and it heats up, but it also flattens down and rotates. Right? Is that the big cloud had some angular momentum. These particles might be moving at maybe a few centimeters a second, but the angular momentum is the mass times the velocity times the radius, the distance away from a point it's rotating around. So something moving at a few centimeters a second over a cloud size, which might be a light year across, it's going to have a huge angular momentum. And so when it collapses down to solar system size, it speeds up all of those particles and they start orbiting faster and faster. And so this is Kepler's third law is saying stuff very, very, very far away orbits very, very, very slowly from the center of this thing. As it collapses, it speeds up. It has to speed up. It goes faster and faster. So it's conserving angular momentum. So that explains the rotation, but it doesn't explain the flatness completely. And there are going to be collisions between the particles in the cloud. And in the beginning, the cloud is particles moving in random directions, but the cloud may overall have some net velocity, some net rotation. So as it collapses, collisions that are in the direction of the rotation are just going to make more rotation that way. While collisions between particles in the other directions, well, they're in random directions. They're going to average out to no rotation. And so as the collisions occur, generally the random motions are killed off, but the rotation around the center is going to increase. And so you generally get a flattening effect. The cloud flattens down to a pancake that rotates around. And that's going to be a trend throughout the universe is things tend to form small flat disks when they collapse. So we can see this in other stars. Here's a star that's beginning to form. We think it has a planet around it, but we can see the disk that's formed around it. In this case, it's the diagonal yellow streaks is indicating areas where the cloud's cooling off. It's radiating infrared light to us, and it's showing it as in a small disk. And here's another one. Here's where there's some companion stars, and then here's a star that's been blacked out, and we can see the disk around the star. Of course, it's not ideal. It's a black and white image that we've colorized to show detail. So why are there two types of planets? Well, why are they where they're at? That's another question. Why are the Jovian planets so far away? Wouldn't it be cool if they were like nearby and you could see them up close? So we have to talk a bit about what's in the solar system, what's in the solar nebula. And the very, very first clouds are going to be only hydrogen and helium. Because that's effectively what is in the Big Bang. What forms is almost completely hydrogen and helium. But clouds that have formed from old stars dying are going to have heavier metals. So in astronomy terms, metals are anything that isn't hydrogen and helium. So it includes things that absolutely are not metal. But there'll be hydrogen compounds, which is hydrogen forming a compound with something else so that it can make an ice. Right? So those occur in a fair amount in a solar nebula. There's a fair bit of that. Then there's going to be some compounds of basically the four big elements is hydrogen, carbon, oxygen, and nitrogen to form compounds. And so you'll see some compounds of the other stuff, which makes rock. And there's not very much of that, but it's more common than metal, which will also show up. And note the condensation temperature, which you can think of as the melting or boiling temperature, is hydrogen and helium are always going to be a gas. The hydrogen compounds will only freeze at about 150 Kelvin. And that's water freezes at 273 Kelvin. But things like methane will freeze at like 40 or so Kelvin. And we're talking also in space without pressure. So what we're talking about is a rough estimate of hydrogen compounds freeze at a couple hundred Kelvin. Rock, however, well, if you tried to melt a rock on Earth, you can see how kind of difficult that is. Minerals are pretty stable, and so the temperature has to be fairly high, 500 to 1500 Kelvin, let's say. And then metals have very high boiling points or high condensation temperatures. You're going to find those at temperatures over 1000 Kelvin. And it kind of depends on what the metal is, of course. And so here's some additional, so at pressures that are believable for both, a solar nebula and for planets that are forming, these compounds will have different condensation temperatures. And basically, it's going to give you an idea of where stuff can form in the solar system. Right? So what's happening is very near the sun, it should be very hot. Only the stuff that needs the highest condensation temperature can be solid there. But as you go outwards, you get lower and lower condensation temperatures, and so more and more stuff can form. Right? So very, very near the sun, say Mercury, you're going to have lots of metals forming. And as you go outwards, Earth and Mars, it's going to have lots of rocky material. Maybe a little water and other stuff will be there, but it'll all be gas. As you go further out, at Jupiter and Saturn and outwards, you'll start getting water ice. And at Saturn outwards, you'll get ammonia ice. And so the further out you go, the lower the temperature drops. And so the more stuff can freeze out, the more stuff can be available. And so that gives us a concept of where the hydrogen compounds form. It's called the frost line. Inside the frost line, you're going to get rocky objects because the hydrogen compounds can't freeze. They can't form form solids. Outside the frost line, you get uh, lots more ice compounds forming because it's cooler out there. So the terrestrial planets formed from what was there, which is particles of rock and metal. And so these particles are going to accumulate, they're going to clump together, and eventually they get big enough that gravity pulls them together into the planets. Um, so from the very beginning, the very small particles are going to stick together, they're going to clump, what's called accretion, and they're going to form planetesimals, which is small portions of, you know, small planet-like things that the things that will form planets eventually. And once they're large enough, gravity can start forming them together to stick together. And the whole process of the clumping and then the gravitational attraction is accretion. And so you end up with lots and lots and lots of small objects, eventually forming just a few very large objects. So the Jovian planets can do the same thing, but there's more stuff because they're further out. They get to experience more of the solar system, more of the cloud. Their orbit is larger, so they can attract more stuff. Also, they have more stuff because they have access to ice. They have hydrogen compounds, so they tend to grow larger, rocky, icy planetesimals until they're about 5 or 10 Earth masses. At that point, they're large enough that they can gravitationally hold on to hydrogen. So in the so throughout the solar system, there's hydrogen and helium. But for the terrestrial planets, they're too small. They can't hold on to it. We can talk about that. Basically, when we talk about atmospheres, we'll talk about the escape velocity for gases. It's just the escape velocity you learned in chapter 4. But we also talk about the speed of gases, speed of molecules in a gas. And so for stuff near the sun, the gases are warmer and the planets are smaller. There's insufficient gravity. Whereas when we go out to the Jovian planets, they get large enough that they can hold hydrogen and helium. And the next slide here actually talks about the molecular speeds of gases. Is the speed of a gas is a function of the temperature and the mass of the gas. So for things like hydrogen and helium, they can move at a much faster speed, which means they can escape a planetesimal. So you need a larger planetesimal to create a larger escape velocity and hold on to the hydrogen and helium. And we'll talk about that more because it's not completely the way it sounds. Is most gases, if we had a lot of hydrogen in the atmosphere, it wouldn't leave all at once. It would slowly leak away. So only a few particles would get fast enough. But the particles are always exchanging momentum. They're always bouncing around, colliding with each other. And so some of them would end up with enough speed and get away. And so it would be a very slow leak. But a slow leak over a long period of time means there's no hydrogen and helium on terrestrial planets except what's already in compounds. So we can also ask, where is that hydrogen and helium today? The cloud should still be there. It didn't pick everything up. And there should be other rocks and stuff, you would think. And so if we were in person, I would spend some time talking about the ability of light to move particles, which is kind of an odd thing, but light has momentum as well as energy, and it can collide with objects and transfer momentum, and so objects can be pushed around by light. And that's what happens with the sun, is there's light coming off of it, and there's a solar wind, outflowing particles from the sun. And those things are going to push away the leftover gases and some of the smallest of the leftover rocks and dust. And we figure that the sun probably rotated a lot faster and was more energetic, and so there might have been a stronger solar wind. And we're comparing young forming stars that we see now and how they act, and that's trying to inform us of how we think the sun acted. So we think the young sun rotated awful fast, but the sun also had a strong magnetic field, and that interaction between the field and the nebula probably moved the particles around and slowed down the rotation of the sun over time. So, what are asteroids and comets? Well, for one thing, we talked about ices forming. That's comets, is balls of ice. We talked about rocks forming the rocky planets, planetesimals. This looks like what asteroids are. Asteroids and comets seem to be leftovers from the accretion process. And what we get is rocky asteroids form inside the frost line, and icy comets form outside the frost line. I have sent you some stuff. I don't know if it's in the past or in the future at this point, or if it's concurrent. I've sent you some stuff on. You can have mixtures. You can have things that are both rocky and icy, and the dividing line between asteroid and comet isn't completely perfect. It's got a band of a gray area. Basically, there's different types of objects. One class was what we called centaurs, is objects that kind of have characteristics of a comet and an asteroid at the same time. They orbit in different places, and they appear to have different features based on where they are in the orbit, and it's kind of interesting. And there's other things like that. So that's why we talk about small objects or small bodies. Is not everything's a rock or an ice ball. Some of those planetesimals, the planets are going to be mostly formed and basically vacuum up the remaining planetesimals that it can reach. And so there's going to be a heavy bombardment. There's going to be lots of impacts occurring on the planets. And we see evidence of that in the rocky planets. Is we see some that are very heavily cratered, and that cratering is going to come for a fair bit during this heavy bombardment. And we think that some of the impacts are going to deliver water to the Earth. Is that not everything that impacts the Earth is going to be rocky. Some of it's going to be water. And so it's going to provide liquid water essentially by melting. So the exceptions. Well, we've already talked about bombardment, but there's some other exceptions, right? We think rocky terrestrial planets really shouldn't have moons. And we think that what's happened is, for Mars, those moons are captured. Because they basically look like captured asteroids. They look like rocky potatoes. Our moon's a little bit of a different thing to explain, but our big hypothesis now is that there was a giant impact, that basically the Earth formed, and then one of the remaining big planetesimals hit it and knocked off a lump of, or knocked off a band of material that happened to coalesce and form as the moon. And there's a reason to think this is, when we look at the moon, it doesn't look like the interior of the Earth. It looks like the outer surface. It has a, it looks like it might have been knocked off the surface of the Earth. Rather than being formed at the same time as the Earth, right, is if it's formed at the same time, it should have about the same composition because it's drawing from the same material. But if it's formed later from a collision, it's going to form from the top layers of the Earth's surface and whatever this planetesimal is. So, being poor in metals and more enriched in minerals is going to be sort of a natural thing for a planet forming in for a moon forming in a collision. And giant impacts, we think, explain other things. Like we think Venus's rotation is effectively slowed by a giant impact that hit it the correct way. And so adding the angular momentums ended up with no net momentum, and it has a very slow rotation. For Uranus, hitting it just so can tilt it over, turn it on its side. And it may be several large impacts, maybe, that sum up to this. But it's like we basically think that impacts are doing a fair amount of the explanation for the exceptions to the rules that we've stated. So this is the thing is we've come up with a theory and we've tried to make that theory explain the formation of our solar system. But it's just so theory is we're describing one solar system. And we've kind of found some new information. We've looked at planets around other stars, solar systems around other stars. And that means that maybe there's some problems with our model. And, we described it in a way that the formation in our theory seems inevitable, but, maybe the details aren't the way they look today. Maybe there's some changes to it. So the last thing is, how do we know how old the solar system is? Well, how do we know anything that's old is old? Generally comes down to radioactive dating, radiometric dating, looking for the formation of elements that form through radioactive decay. And we do this a fair bit, it's called carbon-14 dating, when we date stuff that is likely to be seen on Earth and seen, in over a few thousand years. And for other things that are older, we use other elements like potassium or uranium or something like that. And what we figure is moon rocks are about 4.4 billion years old based on dating them radiometrically. And then so meteorites are about 4.5 billion years old. And so we figure that the formation is likely about 4.5 billion years old. So how do we actually do that? Well, in a rock, you could have an unstable element, say, in this case, potassium-40. And over time, it's going to decay. And when it decays, it's going to form a new element, in this case, argon-40, which happens to be a gas. But, maybe it's trapped in the rock. Or maybe it's not potassium and argon. Maybe it's uranium and another element. Thorium. Thorium would probably be the next thing it decays into. What's going to happen is, over the life of the rock, it's going to decay, and what we find is it's an exponential decay. Exponential decays have what's called a half-life, the time it takes for half the stuff to decay. So over one half-life, in this case, 1.25 billion years, half of this potassium-40 will decay and turn into argon-40. Well, over the next half-life, so 2.5 billion years, so in a second interval, you'll get half of the remaining stuff, which means you burn half of it in the first half-life and then a quarter in the second half-life, so 3/4 total have converted. And then 3 half-lives later, you've burned a half plus a fourth plus an eighth, which is 7/8. And so by measuring the fraction of potassium-40 left compared to argon-40, or often the fraction of potassium 40 left compared to other elements that would form concurrently, you can figure out the approximate age of a rock. So that's kind of where we kind of end up there. I do have a little more to say, which is how do we measure the age of meteorites? Well, they land on Earth. We go pick them up and measure them. But that's kind of an interesting thing in and of itself. How do we know that a particular rock we pick up is a meteorite? Well, one way is that meteorites meteorites formed in the solar nebula. They're remnants of the formation, and so they have a different makeup than rocks that have weathered and eroded and formed on Earth over and over again. So rocks on Earth tend to be fairly new, whereas meteorites tend to be fairly old. The other way we know that rocks can form is we can go pick them up in places where we see them easily. We look for a place where we don't expect rocks to be, and then when we find rocks, we know they've fallen out of the sky. And that sounds a little ludicrous, but think about it. You're looking for a dark rock. You want somewhere where you're not going to see rocks and where it's going to stand out. It turns out snow is a really good place. And so a lot of meteorites we found is in Antarctica, where there's permanent snow. There's not going to be anything to disturb other rocks and generate rocks on top of the snow. If you walk around and you see rocks that have landed on the fresh snow or on the several years old snow, you're fairly certain it's a meteorite. And then you can measure its age and you can figure out, yeah, it is. And so we found a lot of stuff by just picking up meteorites and measuring their ages. So that's going to conclude the video here. That's chapter 8. Yeah, chapter 8 on formation. So on chapter 9, we'll talk about geology. And we're going to start with the terrestrial planets and talk about the geology of the 5 big objects. And then we'll talk about their atmospheres in the next chapter, in chapter 10. And 11 will be the Jovian planets. 12 will be small objects. And I think 13 will be objects outside the solar system. And that should hopefully finish the chapter. So let's see how we do. That's going to conclude this video.